Right, so I think we're good to get started here with our second talk of the day. We are happy to have Annie Bronzi, who's also one of the organizers of this workshop. She's speaking from the University of Campinas in Brazil, and she's telling us about giving a talk on the Euler equations with helical symmetry. Thanks, Annie.
Thank you very much, Cecilia, for the introduction. And I would like to thank the other organizers for this opportunity to talk about my work here. So today I'm going to talk about the Euler equations with the Helicosymmetry. This is joint work with Helena Nussensweig-Lopes and Milton Lopes Filho. Actually, I'm going to talk about an old result and new developments on these helical flows. Okay, so let me start just recalling some of the properties and known results for the Euler equations. So this is the system, the incompressible Euler equations. Let's see. Okay. So U is the velocity field, P is the pressure. So it's very well known that for dimension greater or equal to 3, we have only local well-posedness in HS for S bigger than n/2 plus 1, and the global well-posedness is still an open problem. For dimension 2, we actually have the global well-posedness in HS for S bigger than 2. Regarding the existence of weak solutions, so we have also the Navier-Stokes equations with a term here, which is a dissipative term. For the Navier-Stokes equations, we have the global existence of weak solution for initial data in M2 from the work of Leray back in the 30s. So, but for the Euler equations, this was solved for very recently, 2011 by Wiedemann, but in the context of wild solutions. So for initial data in Ali2, using these methods from wild solutions, he was able to prove the global existence of a solution, but they are very, very irregular. Okay, so regarding the study of the Euler equations, there is this quantity, this physical quantity, which is the vorticity, which is the curl of the velocity, which plays an important role in the study of the solutions. So if you take the curl of the equation for the velocity, this first equation here, we get this equation. So this evolution of the curl of the vorticity, the curl of U. This is in 3 dimensions. So in the case the dimension is equal to 3, we get this equation, and this term here is which we'll call vortex stretching, and this is this term is this term is responsible for the vortex stretching, and in dimension 2, this term vanishes. So we don't have this term here, just have this transport of a vorticity. Okay. Also a well-known result by Bill-Katmaida is this continuation criterion. So if we start with this a solution in HS for S in this range here, and let T star be the maximal time of existence of U within this class. Then that this quantity will be equal to infinity if T is finite. So the time of existence depends on the control of this this L infinite norm, the integral of the L infinite norm of the vorticity. Okay, so this is why at this point the vortex plays an important role. what happens is that for dimension 2, since we don't have this term, we actually have that if we start with regular NOV initial data, then the vortice, the infinite norm of the vorticity will be controlled. So in 2 dimension, with this criterion, we pass from the local oppositeness to the global oppositeness. Okay, but there are other symmetries that allow us to control this vorticity. So one is the planar symmetry, which is the 2D case. And we also have the axial, the axisymmetric case. So here we need an extra condition that we call the no swirl. So there is, so if you have, if you write your velocity in cylindrical variables, then you take the tangent component of the velocity, and you impose that this is 0. So this is the case where we have no swirl for the axisymmetric case. And under this hypothesis, Maida and Raymond proved the global oppositeness of smooth solutions. And Chai and Kim proved the global existence of weak solution for initial vorticity in LP for P greater than 6/5. There is another symmetry which allows us to prove global oppositeness or global existence of solutions, which is this Helicosymmetry. I'll talk about this in this talk. So this first, at least the mathematical result on these helical flows was due to Dutroy in 1999, and he proved the global oppositeness for smooth initial data on bounded domain. And a little bit more recent, not so recent anymore, but in 2009, Ettinger and Teet proved the global existence and uniqueness of weak solutions with bounded initial vorticity on bounded domain. Okay, then in our work with Helena Nunes-Weig-Lopes and Milton Lopes Filho, we tried to somehow generalize this result. Actually, not generalized, but we studied this problem on the whole space, on bounded domains. Okay. And also the vorticity will be more irregular. It's not so regular as L infinity. Okay, so let me talk a little bit about the Helicosymmetry, and then I'll talk about the result we obtained. So the Helicosymmetry is just the superposition of rotation and translation. Okay, so this is the matrix that represents a rotation around the z-axis by an angle of theta, and this is the translation. So we add the rotation with the translation, and this will allow us to define the Helicosymmetry. So a vector field U is helical if it satisfies this condition. So the velocity at a point, let's say we have a velocity at point X, then if you go around these helices, then the velocity will be just a rotation of U of X. Okay. So here, actually, there's this video on YouTube, but I'm not able to play here. I tried early, so it's not working. But I don't know. There is this video. It's very short. It's like in 9 seconds, and it's just this. So this tube here has a membrane. So this one actually would make the water do this helical movement here. Okay. But just to show at least a video, but unfortunately it's not working. Okay, so we will need also this condition on the swirl. In this case, the helical swirl is also the tangent component of the helices. So so if you take this tangent component, which is u dot psi, then this is the swirl, and then we are assuming that this function here is 0. And now our work. Okay, so under this condition of helicosymmetry and no swirl, we reduce the vorticity equation to a more simple. Actually, under this symmetry, the vorticity equation has a different form, a simpler formula in some sense. So first, the vorticity is the curl of u, but due to this symmetry, we have that omega is given by the third component of the vorticity on this direction here, which is the tangent direction, tangent to the helix. And the vorticity equation, so this is the stretching term, and now it, due to the symmetry, has this form here, given by this matrix applied to u and the third component here. And in particular, because this last component here, actually the last line and the last column is 0, we have the third component of the vorticity. If you see what is the third component, the third equation of the system here, it's just the transport, the pure transport of the third component. And this, and also we can recover all the vorticity, the whole vorticity, using this term here. So this is the key. This is what makes possible to control the vorticity and to get the global existence of solutions. Okay, as usual, we are going to look to the Biot-Savart law, which is the law that, so we know that the vorticity is the curl of u. Now I want to write u in terms of the vorticity. Then you use the Biot-Savart law. So we have the Biot-Savart law in R2 and R3, in the whole space and bound domains. We have this representation for the Biot-Savart law when we impose the periodicity with respect to the third component. Because when velocity field is helical, in particular, it is also periodic on the third component. Okay, so if you, this is actually an elliptic system. So if you inverse this elliptic operator, you can get the representation of u in terms of the vorticity, and the kernel here is given by this monster. And so in this first work that we did, so this is the main ingredient. It was to estimate this kernel, because then using these estimates that we use the standard argument to obtain existence of weak solution. So we got this estimate for this kernel. Okay, so this is just the vorticity equation that I already told you about. So let me just give the weak formulation. So the idea is to work with the vorticity equation. Then to obtain the weak formulation, we just multiply by the test functions and take the derivatives and put it on the test function. And then we obtain this weak formulation. And you need some assumptions of regularity on the functions here. Okay, this is very standard. Then, so this H here is given in terms of the kernel. And what it is actually that we take the kernel and we symmetrize the kernel. With this, we can gain a little, actually we take off a little bit of the singularity that we have at the diagonal. And we were able to prove this result here. So if we start with initial vorticity in LP, periodic in the third component, and assuming that it's compactly supported on the plane, and the P is greater than 4/30, then there exists a weak solution for the vorticity equation, and also we can recover the velocity field, and the velocity is a weak solution of the Euler equations. So the idea is just to mollify the initial data, is very standard. Then we obtain a sequence of solutions for this sequence of initial data. And then we use the local positions for the 3D Euler equations plus the Helicocymeter criterion, because at this point we can control the vorticity. Then we have the global opposedness for this case, and then we prove the convergence of the sequence of solutions. This is actually a point that we have to be very careful. There are a lot of estimates we need to do here, but this is standard. And then we prove that the limit is indeed a solution to the problem. Okay. All right, but then some years later, Jiu, Li, and Niu were able to prove the same result, the global existence of weak solutions with Helicosymmetry and without swirl on the whole domain, but assuming that the vorticity is L1 and LP for P greater than 1. Okay, so they improved our result. So one problem here is because of this 4/3 that we obtained here is because of this estimate that we have in the kernel. We couldn't improve this because this is the better we could get from the kernel. They did something a little bit different than us. They used more the symmetry of the flow, and they used the regularity elliptic theory, but still they used the kernel. Okay, but even though they managed to improve the result. Okay, if we see what happens in 2D, we have this work by Delors in 1991, where he proved the global existence of weak solution for the 2D Euler equation with initial vorticity about the measure and h minus 1. I don't know, there is no p here. Sorry, there is no p. Okay, so we are trying to push the result as close as to this space here. Okay. We were not able to do this yet, but we could improve a little bit this result. So let me explain how we did this. So we used, as in this work of Julie and Niu, we used the symmetry in a clever way. Okay. So from this tools from this paper of Lopes Filho, Ana Mazzucato, Niu, and Helena Lucas Lopes, and Titi. So we have that under these conditions on the Helicosymmetry and the no swirl. So actually, there's a lot of things written here, but the point is that if we know what the velocity field is on the plane, then we can transfer this information. Actually, we have the information on the whole space because we just move along the helices and we rotate the vector field. Okay, so this is the way, a different way of writing this, And when you see this, you can write I'm just coming, let me go, no, here. So you can write U as this rotation of U, of the rotation of the two first components of X. And here you put nothing, okay? Doesn't depend on the third component here. So if you call V, the first two components apply just to the first two variables and put a 0 on the third variable, the X, so you are at the plane. So you have the information on just the first two components of the vector field U, only on the plane, then you can recover the whole velocity field U. This is what is stated here, okay? And for the vorticity, you have something similar. You just need to know what happens with the third component of the vorticity on the plane, okay? Then you can recover everything. So, but you also have this third component here is the grad perp of V, or in other words, this is the curl, the 2D curl, because here we are on the plane. So it's the curl of V. Okay, so when we are working with the Euler equations in 2D or 3D, you have that the velocity is divergence free. Then you can have, then you can introduce a stream function and use the conditional the equation, the relation with the from the vorticity with the velocity to obtain the condition to write U in terms of the vorticity. Here we don't have that this V, this capital V, is divergent free. It's not, okay? But even though we can introduce a stream function, this was done in this paper of Etziger and Tita in 2009. And so this stream function introduces so psi, the grade pair of psi is this matrix here. It depends only on y, and the function, the velocity field v. And a simple calculation, if you take here, you can write v as the inverse of this matrix times the grad pair of psi. And if you take the grad pair, the grade pair inner product with v, you obtain this term here, which is the divergence of this matrix given in terms of h times the grad of psi. So in other words, you can write, this is nothing else than the vorticity, this capital omega. So this is a second order elliptic operator. So this guy here, which I call L, is a second order elliptic operator. And then you can write omega in terms of psi, the stream function. And then you can recover velocity from omega, okay, using this formula here. All right, and under this this vanishing, this helical and no swirl condition, we can rewrite the Euler equation. So actually, if we start with the solution U of the Euler equations, which has Helicosymmetry and no swirl, then you obtain this equation for omega and psi, okay, which satisfies this relation here. Okay, then what we try to do. So actually, I think I don't have that much time. So we are going to work with this equation now. But then we can use the Biot-Savart law in R3, and you can use the symmetry and all the conditions here. We can symmetrize that kernel, and we arrive at something that reminds what we have in the 2D case. But in the 2D case, the key ingredient is to prove that this term that multiplies omega times omega is L infinite. But for the helical case, it's not. But it will obtain a bound in terms of the logarithm of the difference x minus y. And then this gives us the idea to work with Euler's space. Okay. If you try to do this with this condition here, we are going to arrive at a condition that to work with this Euler's space, we need alpha to be greater than 1. Okay. And just a remark is that this is an improvement on the work of Lee and Du, because LP is a subset of this Euler's space on bounded the domains. Okay, but then this is very nice. There are a lot of calculations that we did here, but then we tried a different approach, which is much more clean and actually improved the result. So we were able to push the result to this Euler's space here, L log L to the half. And just really quick, let me say what was the key idea here. So again, we are going to use very strongly the helicosymmetry. This was the problem in our first work, because on the Biot-Savart law, we didn't use the helicosymmetry. We just used that was periodic in the third component. But now make use of this symmetry. We work with this velocity on the plane and the vorticity also on the plane, and we can use the div curl lemma. So this is the version that you used from this paper of Lopes-Filho, Lopes, and Tedmore. We applied this in 2D because we are looking at the velocity field just on the plane, because then we can recover the velocity on the whole space using this velocity here. So the first condition that we needed to verify is that the velocity field converges weakly in L2, but this comes from the conservation of energy. Then the condition that the initial data is in L log L to the half, we obtain, and using that this Euler's space is a rearrangement invariant space, we have the conservation or the boundedness of the vorticity in this space. And using that the space is compactly embedded in H-1, we have the pre-compactness of the vorticity in this space, which is the third condition here that we needed to verify. And the second condition, we just make the calculations here. You can write the divergence of Vn is not zero as in the real 2D case, but even though we obtain in terms of the the derivation of the stream function and the gradient of the stream function, but then we have the elliptical regularity theory for this space, for this Euler's space, and then we obtain the pre-compactness also of the divergence of the velocity, and then applying the div curl lemma, we obtain the convergence of the square of the velocity in the sense of distributions. Then we can recover the velocity from this velocity on the plane and obtain that the whole velocity on the space converges the modulus of the velocity squared converges to the model of the velocity squared in the distribution sense. And then, but we have that that UN, the smooth sequence of solutions converges to U in L2 because of the energy estimates that we have. But then together with the convergence in D prime, we obtain the strong convergence in L2, and then we just pass the limit in the weak formulation and we prove that we get the existence of a weak solution for the Euler equation. And I'm sorry that I passed a little bit my time. Thank you for your attention.
All right, let's thank Annie for this nice talk. Now, does anyone have any questions, Giovanni? So if I may ask, there's maybe a silly question, but maybe I missed that in your talk. When you're talking about the no swirl, is there a mathematical condition for that? Is that expressed mathematically or?
Yes, yes. So okay, here. So this is the condition. U dot C has to be 0. And C is the tangent component to the helices.
So is this what's making the solution be given in terms of that third component of the vorticity? Or?
Yes.
Okay.
This with the helicosymmetry. We're able to yes.
Okay.
Right. The vortex just in terms of the third component in this direction here.
Yeah, I was just thinking if there was any way of having a little bit of swirl, but I don't even know how to go about that.
Yeah, things with swirl are harder. So even for the axisymmetric case, there is this condition also to guarantee that the solution is well posed, the problem is well posed. And this case is the tangent component to the circle.
I see. All right. Are there any other questions to Giovanni? I guess if not, then we will go to our lunch break now. Sorry, let's thank Annie again for this nice talk.